welcome to College Algebra. This is section 6.2 with Rob Reynolds. Today we're going to be talking about inverse functions. And inverse functions literally mean every time you see an x, write a y, and every time you see a y, write an x. So we're going to look at some inverse. So one of the most common inverse functions is the logarithmic function. It's the inverse of an exponent. So the inverse of addition is subtraction, the inverse of multiplication is division, and the inverse of an exponent to undo this exponent, which happens to be a variable. Now, if it wasn't a variable, to undo x squared, yeah, you'd take the square root of it. So the inverse of squaring is square root. But the inverse of a variable, which is an x, you can't take the x root of it, so we come up with another function called logs, and logs will undo variable exponents. The interesting thing that I wanted to point out to you was, if it truly is an inverse, then there's going to be this nice line of symmetry. It's always about y equals x. And we'll get to those graphs in a moment. One other thing, if the function is the, let's talk about exponential functions, which we're going to be graphing exponential functions in 6.3, and 6.4 we're going to be graphing the log functions. But just taking a look at this, the vertical line test, yep, it passes on the function. Well, instead of graphing the inverse function, which is this log function, and checking to see if it also passes the vertical line test, you could always just use the horizontal line test on the original function. And if the horizontal line test passes on the exponent, then that means that the vertical line test is going to pass on its inverse, which is the logarithmic function. I'll explain that again in just a moment. So looking at this, is this a function? Yes, it is. For every x, there's only one y. But this is a special function because for every y, there's only one x. So we call this a one-to-one function. Not only does the vertical line test pass, but also the horizontal line test passes. And although this dog, duck, duck, pig, rabbit function, that's a function, it sure is, but notice it's not reciprocating, so it's not a one-to-one. Because for every y, there's not just one x. For this 11, it's going to two different x values. You can't do that. If it's a one-to-one, not only does for every x there's only one y, but for every y there should be only one x. So looking at what a one-to-one is, it's a one-to-one. That's exactly what it means. For every x there's only one y, for every y there's only one x. So this is not a one-to-one because the y value is going to two different x's, and this isn't even a function because that can't. So this would pass the vertical, the inverse of this is a function, interestingly enough, and this is how you write inverse functions, but the function here is not even a function, but its inverse is a function, which passes the vertical line test. So again, this would be a function, sure, for every x there's only one y, but the inverse is not a function. So again, not a one-to-one function, but this is a function. And then looking down here, if no x's repeat, then it's a function. If no y values repeat, then the inverse is a function. And then if the function is a function and its inverse is a function, we call this a special function, a one-to-one function, where the horizontal line test and the vertical line test passes. So again, here's checking the horizontal line. This is a function. This guy passes the vertical line test. No matter where you draw the vertical line, it only crosses once. But check it out, the horizontal line test crosses twice, and therefore it's not a function. So looking at determining whether these graphs are a function, if we have a graph, we know the parabola looks like this. Well, instead of graphing the inverse function, we can just check the vertical and the horizontal line test. Does the horizontal line test pass? And the answer is no, it doesn't. It crosses twice. And for the horizontal line test pass, you can only cross once. Well, let's look at this graph. We know this is a cubic function, and not only does the vertical line test pass here, but see, no matter where you draw that vertical line, it's only going to cross once. The horizontal line test passes as well. No matter where you draw it, it only crosses once. So this is a good example of a one-to-one function, because not only is the function passing the vertical line test, the inverse, which I didn't even graph the inverse of this, I suppose it's the cube root, but the cube root function is like this walk like an Egyptian, which we studied earlier, kind of function. But you can see that the vertical line test does pass, but without even graphing the inverse function, we can tell that the inverse was going to pass by checking the horizontal line test on the original function. I hope that makes sense. So don't check, don't even graph the inverse. All we have to do is check the horizontal line test to see if it passes, and if it does, then the inverse is a function. So that's the theorem, and that's the definition. So again, state the domain and the range. Well, here the domain are the x's and the range are your y's, and they're just saying, hey, be careful. Here the domain is your population, and your range is your y, so be careful with your definitions there. Find the inverse. I'm not going to write it all out, but inverse literally means for every time you see an x, write a y, and every time you see a y, write an x. The first inverse would look like this. The second inverse would be -8, negative. This is interesting. This guy, the inverse of it, is actually itself. So a point could map to itself, being the inverse. Same thing with the 0, 0, the next point. So you get the gist. Replace your x's with y's and replace your y's with x's. Some of you are really visual people, so we're talking about input and output. Notice this is notation for inverse function, and notice this is kind of what we were doing in 6.1. If we find f at g at x, it should equal x, and g at f of x, if we let the inverse function be g, should also equal x. So this is a good test to see if the function that we found is truly the inverse function. We can just check composite functions, which I discussed in section 6.1. So here they're showing you checking the composite function. If g at x is this, and the inverse function, which we were guessing was the cube root of x, yes, they are inverse functions because why? F at g at x is x, and g at f of x is also x. But instead of saying g at f of x, we're saying, well, this would actually, if we're letting the, well, whatever. If you take the function composite with its inverse, doesn't matter if it's g at f of x or f at g at x, doesn't matter how you define it. So let's take a look at this. Let's find out if f at g at x, by the way, better equal x. We're testing to see if this truly is the inverse function, and g at f of x is also, and I'm going to let this inverse function be my g at x, so we don't have to worry about f prime or f inverse. We'll just call it the g at x function. So just like we did in section 6.1, let's actually check to see if the composite functions both equal x. So here we go, f at the g function is right here, 1 over x plus 1. So go to the f function, 1 over x minus 1, and plug in the value, which in this case is 1 over x plus 1. And interestingly enough, this plus 1 and this minus 1 will cancel. Don't worry about the parentheses, it's just a grouping mechanism. So we get 1 over x, which says take the reciprocal, and sure enough, we get x, which we knew we did, but it's a proof. So you need to write all that out for me. Remember, you need to show your work. I wrote show work on a lot of people's tests on the last test, so it's the work that I'm going to see, and that's what verify is. It's a proof. So I'm giving you the problem, I'm giving you the answer is x, and you just got to show me the meat in between. So go to the g function, which is right here, 1 over x plus 1, and plug in all of this into the g function, 1 over x minus 1. So this time I can't combine the ones, but I can get a common denominator. This is x minus 1 over x minus 1. So in the numerator, I have, it's 1 plus x minus 1, which is just x over, what? I did something wrong. I did do something wrong. Sorry. Let me back up and try this again. This is a plus 1 because of this plus 1. But look at this. Can't we just simplify this? This is 1 over a fraction. Well, instead of divided by a fraction, you can multiply by the reciprocal. And now I can combine x minus 1 plus 1, and that's the 0. So notice that the proof on the left looks different than the proof on the right. I got messed up a little bit. There's how the author worked it out, and sure enough, they got x for both of those as well. All right, so obtaining the graph of an inverse function. Every time you see an x, write a y. Every time you see a y, write an x. And if you do that successfully, you should end up with this nice y equals x symmetry. So they're showing you, here's that y equals x symmetry, and you're just replacing each point, instead of x and y, you're replacing it with y and x. That's what inverse means. Again, checking for that nice symmetry, you can just look at the graphs and tell if they're inverses by checking symmetry. Here's an example. Instead of plotting the point -2, -1, we're going to do the inverse of that, which is -1, -2. I'll call this point A, and I'm going to call this A prime or A inverse. So, and I'll label it -1, -2. Let's do it again. This point here is -1, 0. The inverse of that, flipping the x's and the y's around, is 0, -1. So let's call this point B. So then B prime is right here in blue. I'll label it 0, -1. And then the last point is 2, -1. I'll flip that around to 1, -1, +2. So if this is point C, this is going to be C prime, and I'll label it 1, 2. And so then I've got 3 points, and all I need to do is connect them together. So A is going to B here, so A is going to B, so I'm going to connect A to B, and then B is going to C, so I'll connect B to C, and sure enough, I have the happy face function is my inverse function, and I could see the line of symmetry. It's working pretty good. I've got this y equals x thing going on. If I were to flip that over, the smiley face would fall into the blue, or the blue would fall into the smiley face. So I'm fairly convinced I actually do have the inverse function. And there's the author's solution to that. To find the inverse function, for a defined equation, we're just going to replace y, which remember f of x is y, with x, and replace x with y. But don't leave the answer like this. Let's go ahead and actually solve it for y by subtracting off 3 from both sides and dividing by 2. But don't leave your answer like this either, because in fact I would recommend changing the y back to the inverse function, because we've changed f of x to y, so let's change that y back to the inverse function. And let's not leave the answer like this. It's a little bit confusing. It's a little bit easier to see that that's 1/2 x minus 3/2. So I'm going to try to graph both of these things. I'm going to start by graphing the original function, which says this is the y-intercept. That's a start value. So I'll start at 3. Let me get this graph up just a little bit. So I'm going to start at 3 and then do my slope of 2. So there's the y-intercept, and the slope says rise 2, run 1. And I'll do that over and over and over again and draw a nice straight line with a credit card. Instead of starting at -3/2, I'm going to try to identify some points. This point is 0, 3. This point is over 1 up 5. And to find the inverse, I'm simply going to flip it. Instead of 0, 3, I'm going to plot 3, 0. Instead of 1, 5, I'll go to 5, 1 and graph this in. And there's the inverse function. Very easily drawn. And you can see the -3/2 appears right there, but I'm not going to graph it, and because it's hard to rise 1 and run 2 from a point that's not exactly on the graph. So it's easiest just to take the points off the original function and flip them. And again, if you wanted to check your line of symmetry, that's working pretty nicely. Y equals x should be telling about if it's symmetry or not. So composite functions, this is a little bit harder. This says, let's do the same thing. Find its inverse and then check it. So this is a 2-stage. First of all, we're just given the function y is equal to. This is a little bit harder, so stay with me, because students struggle with this because we're going to end up with 2 y's. Remember, this is a y value, so I'm going to replace that with x. And these are x values. I'm going to replace that with y. And students usually struggle with this because we end up with too many y's and they don't know how to get 1 y out of the 2 y's. So the first thing I would do is suggest multiplying both sides by y minus 1. And then let's go ahead and distribute. Let's see, this side will cancel. So I'm just left with 2x plus 1. But when I distribute this over here, I'm left with xy minus x. Now this is where students usually go bonkers, because I can't subtract 2y off because I can't combine it with it. Well, in fact, let's subtract it off and I'll show you. There's nothing to combine here though. So I'm getting all the y's on the same side. I'm going to add this x to both sides. Again, I can't combine it, so I'll just write out x plus 1. So what do you do from here? This happens often enough where it trips students up. Whenever you see 2 y's, you want to create just 1 y. You're going to have to factor. In this case, we're factoring out y. And then you divide by y minus 2. So I think that the inverse function is this. And I'll replace that with f inverse. But to verify that it really is, I'll need to run a test to check to see if f at g at x truly does equal x, and I need to check to see if f at g at x also equals x. So here's the way that I'll always start all my verifications, and then I'm going to show the work in between. Well, I'll do the first one with you, and then you can finish this up. This says the g at x function, I think I'm going to let be the inverse function, which is x plus 1 over x minus 2. Now this gets difficult because it says every time you see an x, go to the f function and replace it with all that crubba. So 2 times x plus 1, I'm replacing x with parentheses, and then inside the parentheses, I'll plug in x plus 1 over x minus 2 and x plus 1 over x minus 2. This is no easy task. Up top, I'm going to distribute the 2 for a 2x plus 2 over x minus 2, and I'll change this to x minus 2 over x minus 2 because that's equal to 1. All divided by, ugh, it's terrible. All divided by, I'll change this to be x minus 2 over x minus 2, and I'll distribute the negative for x plus 1 minus x plus 2. Be careful with that plus sign, distributing that negative all over its common denominator, x minus 2. And then instead of dividing by a fraction, I'm going to multiply by the reciprocal. So up top, if I combine 2x and x, I've got 3x over x minus 2 divided by, let's change that division bar to a division sign. Oh, it looks like the x's cancel here. So I'm left with 3 over x minus 2. But instead of dividing by a fraction, you can multiply by the reciprocal. So this is 3x over x minus 2 times x minus 2 over 3. Sure enough, this cancels. I'm getting close. 3x divided by 3 equals my x. Again, you're going to have to repeat this process for the right side. I've only done half of this proof, which is f at g at x. Now you need to do the f at g at x and also show me that it equals. So surprisingly enough, these are inverses of each other. And it's kind of interesting because we're saying if you fold this over, this little piece will fall on this piece, and this piece will fall on this piece. So it's kind of interesting why it's an inverse or not. So to find the domain and the range, the domain of this function says, hey, it's all reals except at this asymptote. X can't be 1. That's the only thing that would cause havoc. The range, I'm going to look at the degree of the numerator and the degree of the denominator. Since it's the same, I'll try this a over b trick, or a over c, and either way, it's going to be all reals, but y can't be the horizontal asymptote, which is at 2. Well, this is the domain and range of the function. To find the domain and the range of the inverse function, you don't have to graph it. You don't need to find the inverse function. All we know is that the domain becomes the range, and the range becomes the domain. That's what inverse means. So this was the domain. It's going to become the range, and this pink was the range. Excuse me, it was the, oh my gosh, I have that backwards. Let's try this again. Can't talk and write at the same time. That's bad. So your yellow domain becomes the range of the inverse, and your pink range becomes the pink domain. All I have to do is replace x's for y's. So again, it's all reals, but instead of saying I'll say x can't be 2. And instead of saying y can't be 1, I'll say it's all reals, but y can't be 1. Instead of saying x, instead of replacing x with y, and I'm replacing domain with range. And that way, you don't actually have to find the inverse function to state the inverse function. So again, finding the inverse of this thing, every time you see a y, let it be x, and it's going to be actually the square root function, and you're going to have this nice symmetry, but there's going to be a domain restriction. Because there's a domain restriction on here, we can't let x be negatives, so we're not going to let x be negatives here. So you only have half of this problem. We're not going to graph the other half of the problem, because then it wouldn't pass the horizontal line test, and it wouldn't even be a function. So in order for the inverse to be a function, this to be a one-to-one, we're going to restrict that domain to be greater than greater. So here's a nice little summary of what we've talked about. Multiple choice, yes. No, the vertical line test does not pass. And this one says, let's see, this is going to, the function is going to shift 4 units to the left. So it could be answer A, B, or D, but it can't be this one because this is facing down and it's not negative. But the inverse of this, that'd be easy to find. What's the inverse of negative 4, 0? Well, it would be 0, negative 4, which this one works good. So they're saying this might be the inverse. But this one is not 0, negative 4, so it can't be C. We already said it can't be C. This one's not 0, negative 4, so it can't be A. And if the original function is negative 4, 0, the inverse should be, oh, this is wrong too. I mean, these are all wrong. We only write one for the correct inverse of negative 4, 0 is 0, negative 4, so that green is the inverse of the black function, so I would choose B. I hope that was helpful for you. You email me with questions. Thank you.